So we talked about rate of reactions and the things that affect it. Now we're going to look at this equilibrium concept where the rate of the reactants making products is the same as the products breaking down to make reactants. And again, this is happening in a closed system. Equilibrium only occurs in closed systems because we need to keep it going and let nothing escape into the atmosphere. So a couple things. Remember, there's things called reversible reactions. So we have a reactions in which products can react to reform their original reactants. And we have our example of our forward reaction, hydrogen and nitrogen becoming hydrogen iodide. Okay. And then um, you have your reverse, which is the hydrogen iodine breaking down, become hydrogen and iodine gas again. And then you have a reversible reaction, which means it's going the same way, also known as an equilibrium reaction. Okay? So reactions that don't go to completion and in which reactants and products are present in fixed concentration rates, those are equilibrium reactions. And you can kind of see that here. We have calcium carbonate and water and carbon dioxide making calcium hydrogen carbonate. But that calcium hydrogen carbonate is breaking down to make those reactants again. And the same thing with sulfur dioxide and oxygen becoming sulfur trioxide, and then that sulfur trioxide breaking back down. A reaction is said to be at equilibrium when the rate of the forward reaction is equal to the rate of the reverse reaction, meaning that the reactants are making products at the same speed as the products breaking down to reactants. That's pretty much what we're talking about. The forward reaction is occurring at the same pace as the backwards reaction, the reverse reaction. Couple things. Dynamic equation, molecules of the reactants are being converted to products at that same rate as products becoming reactants. Again, it's occurring at that same rate. Just other ways to kind of think of it, like forward equals reverse. That's the biggest thing to understand about equilibrium. It has to occur in a closed system, so none of your reactants must escape. Some molecules are lost to an environment in an open system. So if we're doing an experiment, sometimes we may lose a little bit as we're trying to close the system off after we put something in. So that's why we need our closed container. And then reactions in solutions don't need a closed container because we're not giving off a gas, as long as they stay in solution the whole time. Okay. So how do we write this? Well, we write it using an equilibrium constant. It's calculated from equilibrium expression, which we're going to look at for reaction using concentrations. We don't have to actually calculate it. That's a little bit higher science that we're doing than what we're doing. But you could calculate it, and there's lots of videos out there to show you how to do that if you're interested. But really, we're looking at the equilibrium concentrations of our products and our reactants from our balanced, remember that balanced equation I told you was going to come back to you. That balanced equation is really important because we're going to use some of those numbers. So that means we need to make sure our equations balance while working through this out. So we can write our rate as an equation known as the equilibrium constant. And here's our example. So little a big A plus little b big B yields little c big C plus little d big D. Okay, so here's our equation first off. Okay, our big letters are chemical formula, so it could be like, I don't know, oxygen O2, it'd be, NH3, okay, whatever A is, that is what we're going to put. So you're just putting the chemical formula of that compound or that molecule. Okay, your little d is your coefficient. That becomes a exponent or a superscript. Okay, your products will go on top and your reactants go on the bottom. So let's take a look. It might be a little bit easier to understand when you actually see this work through. So a couple things before we get started. this reaction, this constant only works for gases and things in aqueous solution. You cannot use pure solids or pure liquids. Okay, so that's really important. While when you look at a reaction, a chemical equation, they put solid, liquid, gas, AQ, because you need to understand, is this important for our equilibrium constant? Okay, so here's our example. This is the one that's in your notebook. I have tin oxide plus carbon monoxide becoming tin and carbon dioxide. Okay, so what I'm going to do, okay, is I need to look at my products first, and I need to see which products would be important. And if I notice, okay, tin is a solid, I can't use him, but carbon dioxide is a gas, so I'm going to use him. So I'm going to write CO2, and I'm going to put in brackets, but notice that I have a coefficient. That coefficient 2 is going to become my exponent or superscript. So if I write it just like that, okay? Now I'm going to look at my reactants. Okay, my iron oxide is a solid. I can't use him, okay? But then notice my carbon monoxide is a gas, so I can use him. I'm going to do the same thing. I'm going to write brackets and put in my chemical formula of CO, but also note that he has a coefficient of 2, and so that 2 is going to become my superscript or exponent, and I put that on the bottom, and that's it. That is my chemical or my equilibrium constant for this reaction. Let's try one more. Now this one's a little tricky because sometimes you're going to look at an equation and you're going to say, well, there is no gas or aqueous solution on this side, on the product side or the reactant side. What do I do? If you do not have any component that you can use as a constant, so everything is a solid or a liquid, there's no gas or aqueous solution on that side, you write the number 1. Okay, you just put the number 1. So let's take a look at this one. I have hydrogen and I have oxygen forming H2O. And in this case, when they form H2O, it becomes a liquid. So I write KEQ equals, okay, I'm supposed to do my products first, but if you notice on my product side, I just have a liquid and I can't use just a liquid, so I'm just going to put the number 1 because I don't have anything, but I have to put something, and so I always put the number 1. Then I'm going to look back at my reactant side, and in my reactant side, I have 2 pieces. I have H2, okay, so I'm going to put him in brackets, and he has a 2 in front, so he's going to get a exponent of 2. But I also have oxygen, which is also a gas, so I'm going to put him in separate brackets, and he doesn't have a coefficient, so I'm not going to put one there for me. So I write it as such. And that is my equilibrium constant. So pretty much that's all you have to do for equilibrium constants. There's really nothing to it. Just make sure you're looking at your different pieces in your reaction.